Right, are we ready? Yeah, is it on here?
잠깐만요. They're elementary definitions. If he comes 10 minutes late, then that's going to be fine.
Alright, so thanks for coming. So today we have Felix's first talk at IDS.
Thank you.
Triangles, please.
Yeah, thank you very much. I'll be talking about joint work with Balogh and Erdős and Dumitrescu. And what I've planned for today for you guys is we will be looking at some questions from combinatorial geometry, and all those questions, they have one common theme, and that is we're going to apply hypergraph Turán results to attack them. So let me first tell you about hypergraph Turán questions, and I would assume many of you are familiar with that. So one of the central objects which is studied in extremal combinatorics is the extremal function. And the extremal function is defined for a k-graph H, and it is the maximum number of edges a n-vertex k-graph G can have while G doesn't contain H as a copy. So H is some small hypergraph, and we're going to see examples for that one, and G is a big hypergraph. And for this question, it often makes sense to look at this scaled limit, which is called the Turán density of H, where we divide by n choose k and take the limit went to infinity. And here we scale it in that way so that this quantity is between 0 and 1. And here's some warm-up. So this is potentially the easiest 3 graph you can think about. It's a single edge, an edge on 3 vertices. So what's the maximum number of edges 3 graph can contain without containing an edge? Well, it can't contain any edge. So the answer is 0, and the scaled limit also is 0. And here on the right, well, it's potentially the second easiest 3 graph. If you want to, this was a clique on 3 vertices, and this guy here is a clique on 4 vertices. So sometimes called a tetrahedron. So tetrahedron is the 3 graph on 4 vertices where all triples are edges. And now we might ask the same question: what is its extremal function and what is its Turán density? And considering that it didn't get too much more difficult, you might be surprised to learn it actually isn't known. So not just we don't know the extremal function, but also we don't know its Turán density. But there are some bounds known, and so lower bound 5/9 and upper bound a little bit more than 5/9, which was proved using the method of log algebra, so computer assisted. And a famous conjecture by Turán says the Turán density of this guy is 5/9, and if you could prove or disprove it, you would even get $500. So my point here is these questions can get tricky quite quickly.
Is Erdős money or is
It's
money?
So I was discussing it with a friend of mine recently, and we both came to the conclusion: if Erdős is not willing to give the money anymore, then we chip in. So I would give 50, and maybe I can convince Piana to also add another 50. And I'm pretty sure we would be able to crowdfund it. Can I take you up on it? Okay. So what kind of questions do you ask about this object? Well, the natural question is, I give you an H, and your challenge is determine its Turán density. Or what you also might be interested, how does the set look like? So the set of all Turán densities of finite k-graphs. So this is a question people look at. And what you also can do is, instead of just forbidding one single k-graph, you can forbid a family of k-graphs. So when I write this curly H, I have a family of k-graph, and accordingly I define its extremal function to be the maximum number of edges in an n-vertex k-graph G, which doesn't contain any of the k-graphs from curly H as a copy. And in the same way, we can define the Turán density of a family. It might get more artificial, but we will later see some combinatorial questions where more hypergraphs will be forbidden. So it pops up in applications. Okay, so this about the hypergraph stuff. I have promised you questions from combinatorial geometry, and maybe you're more familiar with that, so or not. So up to you. Here's a question I like a lot, which is quite famous. It's a so-called unit distance problem. So we have n points in the plane, and during my talk from now on, whenever you see the letter n, it's going to refer to the n points in the plane. And Erdős had asked a long time ago, what's the maximum number of times that the unit distance can occur among n points in the plane? So unit distance is where you look between 2 points, you check what is its distance, and if it's 1, exactly 1, then it's a unit distance. So in other words, Erdős asks, what determines this function? So we have the maximum over all point sets in the plane, and we count how many pairs in the point set are of distance 1 from each other. And it turns out it's also quite a difficult question. Here you can see the history of understanding this function. Erdős himself proved the super linear lower bound and upper bound of big O of n to the 3/2. And Turán similarly proved the small O of n to the 3/2, and Beck and Spencer big O of n to the 13/9. And then finally Spencer similarly and Trotter to n to the 4/3. And also here, I'm quite generous. Here again, there's some money available. So if you were, or I should say other people are generous, not me, I'm not generous. So same price money, proof or disproof that the unit distance function is n to the 1 plus epsilon for every positive epsilon. And I'm showing, I didn't work on this question, so the reason why I'm showing it to you is it highlights a concept which I want to look at after that. And for this I want to look at the original upper bound proof by Erdős, which is a short nice argument which I would like to recall here with you, and some of you probably have seen that. Okay, so I'll prove the original Erdős upper bound for you. And the trick here is to go via graph theory. So we have our point set of n points in the plane, and we will now construct an auxiliary graph, and then we will get some information from that graph. So he said, let's take the vertex set of this graph to be the point set, and we place an edge in that graph whenever 2 points are of distance exactly 1 from each other. And now the advantage is, instead of counting pairs of distance 1, we can count edges in that graph. And then Erdős had observed that this graph cannot contain the case 3,2. This is bipartite graph you can see on the left side. The reason for this is, if you had 5 such points, then for this point you could draw a circle with radius 1 around it, and those 3 points need to be on that circle. But for this point it's the same. So we have 3 points which are in the intersection of 2 circles, but that's not possible. So we know that the auxiliary 3 graph doesn't contain K32. So particularly the unit distance function can be upper bounded by the extremal function of this complete bipartite graph. And then there are some standard arguments which can give you an upper bound of this extremal function. I'm not going to show you how to prove this, because my talk is about applications, not about extremal functions. So I think so far we should be quite comfortable with this, and probably many of you have seen this before. And I'd like to tell you what happened here conceptually. I see this, we have 2 worlds. We have a combinatorial geometry world where the question is being asked, and then we have this graph theory world. And I'm very familiar in this graph theory world, but not so much in the combinatorial geometry world. And the common theme is going to be, will stay for doing the work, it will be on the graph theory side. Okay, so what happened here? We had one observation about 2 circles. Well, 2 circles can intersect in more than 3 points, and we translated this information into the extremal graph theory world, got information about the unit distance graph, and then could invoke and result on the extremal function, and then translated it back to the geometry world. So all work happened here on the right hand side. So let's keep this strategy in mind. And when you have seen my title and also on my first page, you saw the talk is about triangles. We haven't seen any triangles, so let's get to the triangles. Again, we have endpoints in the plane, and we're going to be interested in triangles which are spanned with vertices from that point set. So if I give you endpoints, we will certainly have up to n choose 3 many triangles. And I'm going to be interested in some particular type of triangles. And here's a question which was asked by Erdős and Purdy in 1975. They asked, what is the maximum number of triangles almost congruent to the unit triangle? And I took it in the wording, it is in the original paper by them. And sometimes when you read a particular question by Erdős, then your first task is to decipher what it actually means. So that's what we're going to do first. I need to explain to you what are almost congruent triangles and what is the unit triangle.
Sorry, why up to n choose 3? What doesn't count as a triangle?
Sorry?
Or what are the things which don't count?
It could be on a line, I guess.
Okay.
So if you, so those it's not never going to be an issue during the talk.
Okay.
But because I'm fine with plotting 3 points on the line, a triangle would be fine with that. Okay, want to understand the question? I will first tell you what a unit triangle is. Unit triangle is this guy. So just side lengths exactly once, equilateral triangle of side lengths exactly once. And I say a triangle is epsilon unit if it's almost like that. In the following sense, that all the 3 sides are between, have lengths between 1 minus epsilon and 1 plus epsilon. And now those are guys we can count. I will introduce this function g and epsilon, so it depends on the number of points and this looseness parameter epsilon, and it counts the maximum number of epsilon unit triangles in a point set of size n in the plane. So we take the maximum over all point sets in the plane of size n, and for each of them we can count, we can check every triple, is it epsilon unit a triangle, yes or no? If yes, we count it. And here this function asks what is the maximum possible. And you should first understand what happens if epsilon is getting bigger or smaller. Well, if epsilon gets bigger, you're going to count more triangles, and if it gets smaller, you count less. And what Erdős and Purdy meant was we're now going to take the minimum over all positive epsilons. And notice here this minimum actually exists because the g and epsilon function is integer value between 0 and n choose 3. Yeah, and now we have rephrased that question, determine the function g of n. And they also provided a lower bound construction, which you can find here. You start with a single unit triangle, so side lengths 1, 1, 1, and you take 3 disks of very small radius, put them around the corners, and now you take your endpoints and throw them in there. And you're going to do it as evenly as possible. So when n is divisible by 3, you're going to put here n over 3, here n over 3, and here n over 3. And now we can count how many triangles are epsilon unit, given the radius is actually small enough. And it's going to be all the triangles with one endpoint in each of the classes. So here I calculated for you. It's a little annoying of a formula if n is not divisible by 3, but if n is divisible by 3, you can just you get just the n cubed over 27. So here this is just making sure it's as evenly distributed as possible. All right, and this construction works for every epsilon. You just have to make the radius accordingly smaller. And our result is we proved the matching upper bound, so that we showed that this construction is in fact the right answer. All right, and I hope you didn't forget the things I was telling you about hypergraphs, because that's what we want to use to prove this result. We need one notion of 3 graphs, which I don't really like. I say a 3 graph is cancellative if there do not exist three edges, A, B, and C, such that the symmetric difference of the first two is contained in the last. And whenever I look at this definition, it's not very intuitive for me. Luckily, there's an equivalent formulation of this which I like much more. It turns out a three graph G is cancelative if and only if G doesn't contain a three graph which is called K4 3 and another three graph which in literature is called F5, or the generalized triangle. And you can see those two guys here. So the first guy is up to isomorphism, the unique three graph on four vertices with exactly three edges. And this F5 guy is a five vertex three graph also with three edges in this form. Here a different way of just a representation of those edges. We can maybe check that those are actually equivalent. When you take here the first two edges and you take its symmetric difference, you get vertex 3 and 4, which is contained in the other edge. So certainly there can't be a K4 3 minus in a cancelative 3 graph. And over here, if we take the symmetric difference of the first two, we get 3, 4, which is contained in 3, 4, 5. So certainly there can't be an F5 either. And it turns out those are actually the only ways of having this obstruction. Okay, and here's a result by Balogh, which says the maximum number of edges in a cancellative 3 graph on n vertices is this product we've already seen before. And now it's quite clear what we want to do. We want to use it. And here maybe a reformulation, right? Extremal function of those two guys is these three. And let me mention for the family of hypergraphs, for this family of hypergraphs, this is the extremal example, which looks like the point Z question, but remember this is a 3 graph. So we have a 3 graph with roughly with 3 classes roughly of the same size, and then all the cross edges. So all the edges with 1 point from each block. And yeah, Balogh proved that this is the unique extremal example for this family as well. Okay, so we need a little bit of geometry also, and luckily it's only high school geometry which we need. I want to convince you about a statement of 4 points in the plane. I'm claiming if you have 4 points in the plane, where the 4 points are of pairwise distance at least 1 from each other, so the 6 distances among the 4 points all have distance at least 1, then actually the diameter of the set is going to be a little bit more than 1 square root 2. So 4 points that could be arranged in either of those two shapes. Either they form a convex foreground, or 1 point is in the inside of the convex hull. And well, one of the outside angles got to be at least 90 degrees over here. This means the diagonal is at least length square root 2, because the blue side had length at least 1. This is at least 1, and by the cosine law we get the correct length. And in the other case, we even get something better. We take the point in the center and realize one of the angles is at least 120 degrees, but we know this blue side is 1, at least this blue side is 1. So the red length here has to be, in fact, even a little bit more than that, square root 3. Yeah, but that was an elementary observation. And let me mark here that this scales. So if we have 4 points in the plane with minimum pairwise distance, say A, instead of 1, then the diameter is at least square root 2 times A. Alright, so now we have 2 tools, we want to put them together. Okay, so now the proof for the upper bound of the maximum number of almost unit triangles in the plane. We take a planar point set of size n, and we're going to assume epsilon is small enough for the proof to work. And now we construct an auxiliary 3 graph. So the point set will give us an auxiliary 3 graph, and we do it in the following way. Vertex set is the point set, and now edges of the 3 graph are going to be those triples which correspond to epsilon unit triangles. So this auxiliary 3 graph depends on the epsilon. It gets more edges if the epsilon is larger and less if it is smaller. And the number of edges in this auxiliary 3 graph is precisely the number of epsilon triangles which you want to count. So we can now just count edges in the 3 graph. Okay, here's one observation I'm claiming about this 3 graph. I'm claiming its shadow graph doesn't contain a K4. The shadow graph is an actual graph which you obtain from the 3 graph by placing an actual edge if it's contained in some 3 edge. Right, so maybe if our 3 graph is just a single edge, we would for every pair check is it in some 3 edge. In this case, yes, so here we would have a K3. And I'm claiming the shadow graph can't contain a copy of K4 because otherwise we can take this K4, but since every pair is in some 3 edge, every pair is part of an epsilon in a triangle. This means every pair has distance between 1 minus epsilon, 1 plus epsilon. So now we have found 4 points with distance close to 1, but the previous observation said this can't be. There can't be 4 points with pairwise distance close to being the same. And now I want to conclude from this that the auxiliary 3 graph doesn't contain K4, 3 minus and F5. And the reason for this is, so here I'm drawing the K4, 3 minus for you. What is its shadow graph? We check for every pair is it contained in an edge, and it turns out the shadow graph is actually complete. So it has complete shadow graph, it has a K4. And similar for the F5, I'm drawing the F5 for you. This was sometimes called the generalized triangle. And here, when you look, I'm going to show you the K4. When you look at those 2 vertices, you would get the K4 in the shadow graph. I probably forgot one edge, but I can't see it right now. It's K4. Okay. So this means since those 2 guys have a K4 in the shadow graph, they cannot be in the auxiliary 3 graph, and we can now put everything together. The max number of almost congruent triangles in the plane is upper bounded by the extremal function of this family of 3 graphs, and by Balogh result we get the upper bound we were looking for. Okay, what happened conceptually again? You might see already some similarities. We have this combinatorial geometry world where the question is being asked, and we have the extremal graph theory world where we can invoke some results. I'm standing rightfully on this side because that's where I'm comfortable at. And we only needed one observation. We needed 4 points cannot have pairwise distance close to 1 from each other. We had checked that. That was the only geometry we used. We translated it into the extremal graph theory world, realizing that the shadow graph cannot contain a K4 as a result of this, and therefore the auxiliary 3 graph is this 3, and we invoked Balogh result on the extremal function of this guy, and we translated this information back. So all is even better, not just all the work is here, no, we even outsourced the work. All right. So the unit triangle is just one triangle. We can look at other triangles. So say we have a general triangle with side lengths A, B, and C. We can now ask the same type of questions. So I say a triangle is epsilon congruent to the one I started with if the 3 side lengths differ from the 3 given side lengths by at most epsilon. So again, it's this looseness parameter. And I define the same function as before. I write here C for congruency, and this H function is the maximum number of triangles which are epsilon congruent to the given one in a planar point set of size n. So this function depends on 3 things: the number of points you're interested in, n, it depends on the triangle you care about, and it depends on the epsilon looseness. And the same way as before, we want to figure out what happens if we take the minimum over all positive epsilons. And what I want to ask is, determine this quantity for such an arbitrary triangle. And the first observation we should do is, if I give you two triangles which are similar to each other, so in this scaling sense, then the answer has to be the same. And the reason for this is, if you have an extremal point set for one, you can scale it appropriately and get an extremal point set for the other guy and vice versa. So, for example, the answer for the unit triangle is going to be the same as the answer for the triangles with side lengths 2, 2, 2. So they don't behave differently. Yeah, and our main result is a full characterization. So you can go through our list. You can take your favorite triangle and then you have to check which of the bullet points does it fall into, and we give you the right answer. Let's focus on the red displayed things first. Yes, it doesn't look so nice, but I will try to make the theorem look a little bit nicer in a second. So let's only focus on the red things, because those are going to be the cases. Okay, right triangle, 120, 30, 30 is also a special case. 4 over 7 pi, 2 over 7 pi, pi over 7. And these two guys are going to be special. And then we have some last category where none of these exceptions are happening. Let's, for example, look at the A case, what's happening here. So for the right triangle, I say the maximum number of triangles which are almost congruent to the given right triangle is at most n cubed over 16. And if n is divisible by 4, then we get the exact answer. And for all of the result, we have this divisibility condition. So if we have some nice divisibility condition, then we get exactly the right answer. And otherwise, you would still get the asymptotic result. It's really just a calculation question. If you wanted to get the right answer for all divisibility, you could do so, but it would be quite painful calculation-wise, so we opted not to do that. Okay, so just to get an idea, maybe I asked Tony a question. What is your favorite triangle?
Oh, I see. The type C.
The type C. What was the time? So the point here was, you give me your favorite triangle, and then in the list you can look it up. I couldn't remember this, but what I can remember is this. So what you can see here is the 5 cases. And in each of the cases below, you can see the extremal example. Yeah, here, Tony, like this one. So for 4 over 7 pi, 2 over 7 pi, and pi over 7, the best thing you can do is you can take a regular 7-gon with the correct side length, and again you place disks of small radius around those points, and you take your endpoints and throw them in there. And here, for this configuration, you do it as evenly as possible.
So I have a question. So let's say if I have a triangle which is very close to right angle triangle, then
you are in this case then.
Yeah, so the bound will be different.
Yes.
But intuition is like it shouldn't be very far, right? So
the problem is, as long as it's a little bit different, in the construction I can make the epsilon even smaller than your difference to it.
Oh.
So I have the power of making the epsilon in the construction even smaller. So it is actually that these triangles with lots of symmetry, say, are gonna be doing better in some sense. Now you look at one more construction. For the right triangle, you're gonna work with a rectangle, and you again have 4 disks of very small radius, and you throw your points inside. For this one, something slightly different is happening, and that's the following. So for the 120, 30, 30, we're also going to work with 4 points. 3 of them are on an equilateral triangle and 1 on its center. And the triangles congruent to the given one are going to be the one which have the center included. So in this construction, the center blob is more important. It's going to be contained in more triangles congruent to the given one. So you want to put more weight in here. So for this construction, we don't split up evenly. We put more into the center. Not telling you the actual numbers. But for the other constructions, you put the same number of points, or as evenly as possible, into the blocks.
For case 2, would putting it on regular hexagon beat the arbitrary t? I guess so, yeah. So it's just beating the hexagon. Okay.
Yeah, the hexagon is a little bit annoying. In our analysis, it came sometimes up as like an almost extreme example.
Yeah. It's just that this one is better than the hexagon.
Yeah.
That's it. Okay,
Yeah.
sorry.
Okay, so yeah.
So what if I want to, so I can do all edges of the triangle have the same length, and I can do certain angles. What if I want that the sum over all the sides are always the same length?
Yeah,
Can I
so
also do that?
This question, yeah, it would be called unit parameter question. So here you see it as, I see it as, we don't just count one triangle, but we count a family of triangles, all the ones with unit parameter, and there are some natural ones, say the class of acute triangles, the class of unit parameter triangles, the class of unit area triangles. So there are some, for all of them, some of these questions have been studied and some have not. So for your suggestion, I would need to think about what's happening, but I would think we should be able to figure it out fairly quickly. Very likely it's just going to be the maximizer.
Maybe very quickly in this plus minus epsilon setting.
Yeah,
exact might be much harder.
Yeah, so exactly. So there's always a difference in these almost questions behave different to the exact questions. The exact questions are closer to the unit distance question than these ones are. Also very interesting ones, the exact ones. Okay, here's the strategy which comes to mind, what we would like to attempt. We want to, ideally, the hope is we construct an auxiliary tree graph where again now edges are going to be the triangles almost congruent to the given one. And we would like to find some small pointed configuration which is not possible. And we would like to translate this information into that the auxiliary tree graph doesn't contain some family of hypergraphs. And then hopefully we can invoke an upper bound on the extremal function and translate it back. So that's the hope. Unfortunately, we couldn't make such a proof happening. There's some reasons for why it doesn't work. But let me say though, for some of the bullet points it works quite well. And in particular for the right triangle case it works quite well. So let me go to that case. Here I need to prove n cubed over 16, and you can find two forbidden subgraphs. Don't look at them too precisely. The first one is one with 4 edges on 5 vertices. The second one is one with 6 vertices and 5 vertices and 6 edges. So they get a little bit bigger. So if you want to prove that they are forbidden, you have to do a little bit more of elementary geometry, and it's actually quite tedious to determine those two guys are forbidden. And there's a result by Felix and 1, which gives the extremal function of this family to be n cubed over 16, which then is the same answer as over here. And from an asymptotic result in the extremal, for the extremal question, one can get an exact result. There's some tricks to transform asymptotic results to exact results. One problem here though is the 90-60-30 triangle is right angled, but actually one of the two guys is not forbidden. So if you wanted to do a forbidden subgraph proof, you would have to handle this case separately. That's why I meant the forbidden subgraph is almost working in that case. In the case C, it works perfectly. This was, oh, Tony, it's your triangle. 4 over 7 pi, 2 over 7 pi, pi over 7 prepared for you. The answer is 2 over 49 n cubed, and you would have to work with 3 forbidden subgraphs. Again, it's somewhat tedious to determine that they're actually forbidden. And there's a result by Felix and 1 using Flag algebras, which determines the extremal function of those 3 guys to be 2 over 49. In this case, it worked. For all the other cases, it didn't seem to be feasible to us to work with this strategy. So what are we doing? Okay. Again, we want to identify some forbidden street graphs. There's still going to be some family of forbidden street graphs. But now, instead of working with hypergraph Turán results, I want to work with weighted hypergraph Turán results. And I'm a little bit lying here because the weighted hypergraph Turán problem we will reduce it to has some geometry component to it. So really, there's not this strict separation between those two worlds, this problem should be more a little bit to the center. But I'll tell you what I mean with that. The weighted notion we need to measure somehow, and for this we use hypergraph Lagrangians. So if I give you a 3-graph H, you can define its Lagrangian polynomial. This is a polynomial associated with a certain 3-graph, and it goes the following. You have number of vertices, many variables, and then it's the sum of this product, where we take a product for every edge. So whenever we have an edge in this 3-graph, we take the 3 vertices and its corresponding variables and multiply them. And then we sum up over all edges. So there's a polynomial and n variables, and you can maximize it over the range, over the n simplex being all variables being positive and adding up to 1. And this maximizer, the maximum over that space is sometimes called the Lagrangian. So the Lagrangian of H is the maximum of that polynomial where we evaluate the n variables to be positive and summing up to 1. So if I give you a somewhat large hypergraph, it's quite a tedious optimization you have to run. Here's one example. I give you the K43 minus. This was the guy with 3 edges on 4 vertices, and I now want to calculate the Lagrangian of it. First, this is the Lagrangian polynomial. For every edge, we got such a product. Here another one, and then we sum them up. And the Lagrangian asks for the maximum over positive variables summing up to 1. And it's already annoying because we have 4 variables to do this maximization problem. But a trick you can do here is the variables 2, 3, and 4, they contribute the same, so you can move values around there and justify that they need to be assigned the same value. So this would reduce the question to a maximization question in 1 variables, which everyone can calculate. So keep in mind, so Lagrangian for 4 vertices was already maybe an unpleasant calculation. You can judge for me maybe. Okay, so this is the weighted component we will be working with. And here's our key lemma, which connects these two things. Again, I will be working with an auxiliary 3-graph, but I will be working with an exact auxiliary 3-graph. With this I mean I take the 3-graph with vertex set P, I have some given vertex set, and the edges are triples which are coming from triangles which are exactly congruent to T. So whenever I have this quantity here, there's no epsilon looseness, it is only those which are exactly congruent to T. Okay, and this key lemma here now reduces finding the maximum number of almost congruent triangles in a plane to a given one to the Lagrangian of some hypergraph. So let's go through it. So say we have a given triangle and we have our endpoints, then we claim that there exists a point set Q, and this point set Q is small, size at most 7, such that in the exact auxiliary 3-graph of that small point set on at most 7 vertices, we have some information, that being the shadow graph is complete, or every pair of vertices contained on an edge. And additionally, we get the relationship between almost congruent triangles to the given one and the Lagrangian of that guy. So the answer would be Lagrangian of this exact 3-graph multiplied by n cubed. So there's some advantage here and some disadvantage. The advantage is we now work on few vertices. But the disadvantage is that we have a weighted version. It's Lagrangians which are more annoying to calculate than just summing up things.
So when you say every pair of vertices on an edge of Q or the edge of the T, HQT.
In this 3-graph. So So the exact auxiliary street graph of the small point set. Yeah. So I've prepared a heuristic proof for you, and I've prepared how we want to use it. So I'm going to start with a heuristical justification why this lemma could be true. Okay, so we want to understand the max number of almost congruent triangles to some given one, and we already know this is precisely the number of edges in the almost auxiliary street graph, as long as we choose the epsilon small enough. Since here we had the minimum over all possible epsilons, we can choose the epsilon small enough such that the number of edges in our almost auxiliary street graph from some maximizing point set equals this quantity. So here P is a maximizer. We choose a point set with the most almost congruent triangles to the given one. And here's the relationship to the Lagrangian polynomial. If we take the Lagrangian polynomial from this almost auxiliary street graph and evaluate at every vertex 1 over n, then we get exactly the number of edges divided by n choose 3. The reason for this is in the Lagrangian polynomial, we always had a product of 3 variables, but 1 over n times 1 over n times 1 over n is the 1 over n cubed. And in the summation, we had number of edges many terms. And the Lagrangian polynomial evaluated at something is certainly at most the Lagrangian of it, because those are all positive and sum up to 1. Okay, and now we have something like what I claimed, but not quite, because if we multiply now with n, we have the right thing on the left-hand side, and on the right-hand side we now have the Lagrangian of still the big point set. So remember, P is here still a point set of size n, and we also have the epsilon here. So it's not quite what I was claiming. I didn't tell you about the small point set yet. And what we're doing now is we take a maximizer of the Lagrangian polynomial. We take an assignment of values to vertices, such that if we evaluate the Lagrangian polynomial at this vector, we get the Lagrangian. And among all such maximizers, we choose one with the fewest non-zeros entries. Right, so for one maximizer, you can count how many vertices are being assigned 0, and among all of them, we choose one with the fewest non-zeros. And now one claim is, if you now have two vertices which are contained in an edge in this auxiliary street graph, where both vertices have positive weight, then we can now move weights around. So two vertices not contained in an edge with positive weight, I can move the weight from one to the other. I don't change the invariant, but I can get fewer non-zero entries. So this means this is not possible. So you cannot have two vertices not contained in an edge with positive weight. So this would be somewhat justifying this part here. Every edge is contained. Every pair is contained in an edge. So now I need to tell you how do you get this point set Q actually. We take now this maximizer and throw away all vertices with value 0. All the zeros, they don't contribute, we throw them away. We now get a smaller point set, and that's going to be our point set Q after we do a compactness argument. So we take some limits epsilon small, this will shrink the point set. So we adjust a heuristic here, and the resulting point set you get we call Q. And this point set Q has the property it has complete shadow because of this observation, and the size restriction comes from in this point set we have obtained, every pair is contained in an edge, which corresponds to every pair is contained in some triangle congruent to the given one, but the given triangle has 3 different side lengths, A, B, and C. So the small point set we have obtained is a point set with pairwise distances A, B, or C, and such point sets can simply be not large. And there's a result by Shinohara which says if you have such a 3-distance set, then such a point set cannot be too large. It can be at most of size 7. Okay, so that was a very rough sketch on what is happening. I hope you got some ideas. So if I lost some of you, I apologize. Maybe you can jump back in for how to apply it. Okay, so I chose here bullet point D as an example, and I want to convince you that we can prove it using our key lemma. So bullet point D was either 108, 36, 36 triangle or 72, 72, 36. And here the claim was max number of almost congruent triangles to the given one is at most n cubed over 25. Okay. So we apply the key lemma, we get our point set Q of size at most 7, but the exact auxiliary 3 graph has complete shadow, so every pair needs to be a side length of the triangle, but those two triangles actually only have 2 different side lengths. This triangle also has just 2 different side lengths. So actually the small point set is a 2 distance set, and 2 distance sets can have size at most 5. And we now analyze how this 2 distance set can look like. Say it has size exactly 5. There's just one 2 distance set on 5 points in the plane, which is the regular pentagon. So Q, we would immediately know how Q looks like. Q needs to be the regular pentagon, but then the only thing which is possible is that the exact auxiliary 3 graph is the tight 5 cycle, and for the tight 5 cycle we can calculate the Lagrangian of it. So the tight 5 cycle is some 3 graph on 5 vertices, and one can calculate the Lagrangian, which would give us the right upper bound. We need to rule out the other 2 cases. What happens if Q has size 4? I'm claiming it's not possible because one can check that K43 minus is forbidden for those 2 guys in the exact auxiliary 3 graph, and there is no K43 minus 3 graph on 4 vertices with complete shadow. But Q had complete shadow in the exact auxiliary 3 graph. So Q-grid 4 is not possible. Q-grid 3 is possible, but there's just one 3 graph with complete shadow, which is a single edge. The only 3 graph with complete shadow on 3 vertices is a single edge, and we can calculate the Lagrangian, which is the product of the 3 variables starting up to 1, which is 1 over 27. But notice 1 over 27 is less than a 1 over 25, so we still have the other one of n cubed over 25. Alright, so that's the proof of this bullet point. And here notice I didn't show you some things. I didn't show you that K43 minus is forbidden, that for this you need some small Euclidean geometry checking. I want to show you one more, the exceptional case. This was none of these special ones, not Tony triangle, not none of the others. And the statement here was max number of almost congruent triangles to the given one is at most n cubed over 27. And notice here the unit triangle, the one with side length 1, actually falls into this category. Unit triangle has no right angle. Those are not the angles, those are not the angles, those are not the angles, and those are not either. And then the answer also was n cubed over 27, so it's still consistent with the first result I've shown you. Okay, we apply the key lemma, we get our small point set, which is now a 3 distance set potentially, on at most 7 vertices. And by small painful case checking, one can find 3 forbidden 3 graphs. K43 minus, C53 tight 5 cycle, and a 3 graph called F32. Don't focus too much on what they actually are. I know we have an expert, Brianna, he immediately knows all of them. Okay, I'm going to do the case analysis again, so I will be going through the size of Q. Again, Q could have size 3, but I said before, the only 3 graph with complete shadow on 3 vertices is a single edge, and the single edge has Lagrangian 1 over 27, so we are fine. Q could have size 4 or 5, but this is not possible, because if you go through all 3 graphs which don't contain those 3 guys, then none of them have complete shadow graph. So for this you actually have to take a look at all the 3 graphs there are on 4 and 5 vertices. There are like 10, 20. And you need to look only at those which don't contain those forbidden guys, and the shadow graph will not be complete, so we can't have size Q for being 4 or 5. So 6 or 7 are going to be the tricky cases. But we know that Q needs to be a 3-distance set. And Shinohara did the work for us. There are not that many 3-distance sets in the plane. Here are all of them, on 6 and 7 vertices. I'm not displaying all the distances here. So for example, here, the black edges are of same distance, the red edges are of same distance, and the third color is not drawn over here. And for some reason, I decided to draw here blue and not red. Don't ask me why. So the non-existent edge is always the third color. So we are interested here now in rainbow triangles, because the rainbow triangles are precisely the one with the 3 different side lengths. And when you check the first case and look at the 2 vertices which I marked with a square, then this edge here is not contained in a rainbow triangle. For example, you could complete a triangle like this is not rainbow. You could complete this with this triangle, it's not rainbow. And this edge you can also complete like this, it's not rainbow either. And same for the bottom vertex. So this edge is not contained in a rainbow triangle, and therefore it's not contained in a triangle congruent to the given one, so it wouldn't have complete shadow in the auxiliary 3 graph. So this case falls out. And in fact, this one falls out because this edge is not contained in a rainbow triangle. You don't have to check it, but I'm just telling you, here's the same. This edge is not contained in a rainbow triangle. Here, this edge is not contained in a rainbow triangle. Over here, this guy is not contained in a rainbow triangle, and here, this guy. So those 6 cases we can kill with the same argument that the exact auxiliary 3 graph wouldn't have complete shadow. We are done. We are left with those 2 cases. So let's start with the right one maybe. This is the regular 6-gon with its center, but the only rainbow triangles here are the ones which have a right angle. For example, this one. This is a rainbow triangle. This diagonal is not drawn, it's in a different color then. So this is a rainbow triangle, but all rainbow triangles in this picture correspond to a right angle triangle, which was one of the exceptions. So we are also not in this picture. Maybe over here, but when there are rainbow triangles in here, let me find one of them. This one. Here, those 2 vertices and this vertex is red, black, non-existent. Do you know this triangle? It's your favorite one, which was one of these exceptions. So we are not in this picture either. We can therefore rule out all of them, and we were not in this case to start with. So just by analyzing what can happen in small points. And I'm done with my talk. Besides, I show you a few questions. What are the questions I have? The first one is my absolute favorite question, and I've shared it already with many of you. So for those of you who I've shared it with, I apologize. And it comes to the theme of what Maike was asking for a certain class of triangles. And the class I'm particularly interested in is acute triangles. Acute triangles are those with angles strictly less than 90 degrees. That's my definition of an acute triangle. So all 3 angles strictly less than 90 degrees. There's a family of triangles. And one can ask, what is the maximum number of acute triangles in a planar point set of size n? So for this question, we don't have this almost notion. It just counts all of them. And the reason why I like this question a lot is it has a connection to a conjecture which I've stated in the beginning about the Turán density of K43. It was the tetrahedra. And there I said it is conjectured to be 5/9, and we know it's almost 5/9. I don't know how big it actually is, the difference, but something like that. And one can check is if Turán's tetrahedron conjecture were to be true, if it were to be 5/9, then you would be able to answer this question. But Turán tetrahedron question is very difficult. So my hope would be, since for this question we have this geometry additional information, it is at least somewhat easier. The question is how much easier it is. And the longer I've thought about the question, I came to the conclusion it's probably, unfortunately, rather close in difficulty.
But it doesn't imply this.
It does not imply it, but yeah, my feeling is it's close to equally difficult. So I would be very happy to see a solution for this. And then, of course, one can change the dimension. So all question of look at, you can look at different dimension. Unfortunately, I forgot to include a picture. I had a picture of my nephew, and he was playing with triangles. He has these magnets of triangles, which he can like stick together. And then I was realizing, what is he doing? I mean, we know what he was studying, that we know, but he was holding it up in the air, so he was doing it in R3, not in R2. So this question is then dedicated to my nephew, change the dimension. He was not just doing it on the ground, he was doing it in 3 dimensions. Yeah, speaking of kids, this is an absolute highlight of my talk. Now to focus, I'm not sure if you have seen this. Here's a kid. So, who is this?
60.
It is my advisor, yes. It is my advisor. 1980 something. He has been working on those questions for all of his life. It's proven here. And this picture also comes with a suggestion for our next lunch seminar, because here he was actually competing in a game show. And the video is on YouTube. If you want to see a video of my advisor when he was 10 years old, fighting against other kids in a math competition, then you can watch YouTube or visit that next lunch seminar. All right, thank you.
Thank you. Questions? Yeah.
So you said at some point that you couldn't do it by a family, and then the Turán problem.
Yeah.
In which sense is the like?
So say the problem. I wanna see. We'll go to the picture. Okay. So here, you might think, okay, let's use in this case where we get the n cubed over 27. Let's attempt the Balogh result about the cancelative hypergraph. So f5 and k4 3 or we just need f5 for the asymptotic result. And then you check the triangles. For the unit triangle, f5 was forbidden, but for some of the triangles, f5 is not forbidden. And unfortunately, this exception is quite large for which f5 is not forbidden. But we know there are other families which are a little bit bigger. But then you look at them, you get more triangles where it would work, but there always were like some really trouble ones where I was not aware of a result which gives the n cubed over 27. So probably I could give you some bigger family and you prove the corresponding result. So I'm not ruling it out. It just at one point became too much work and to handle it. So I'm not claiming it doesn't work, but it certainly would be extremely tedious.
Because like the Lagrangian result that you have, we know that for every Lagrangian we have a finite family whose Turán density is effectively that, right? So that family then potentially would be a family that does this.
But it would be quite. So I also looked at the Picot result. But so the forbidden family is not quite clear how it looks like. For like small 3 graphs, you can find them, and so I did not succeed in applying Picot's result.
So the Lagrangian proof that you described would also apply for right angles and these other, like maybe you don't need the forbidden.
It is the Lagrangian worked in all cases. Yes, it works in all cases, and just in some it's easier to work with the forbidden ones because those you had to find anyways for the proof. So in some cases it was just easier to work with the Turán result.
What was can you remind me which was there was some right triangle that was a special case of 30, 60, 90 or something?
Yeah, this was, we had it somewhere here. It was special in the sense that the only 3 graph result I'm aware of where we get n cubed over 16, which the extremal result is a complete 4-partite 3 graph. The only extremal results I'm aware of is this one. Right. There might be some other ones which you can then use to kill this guy. could be possible. So,
So
yeah,
that-
do you know
this
any
is also
ex-
this is also the right triangle that occurs actually in the hexagon.
exactly, and so the issue here is the hexagon, but yeah. That's a good notice, yeah. That's why I said the hexagon was a little annoying, and
I see.
for this one.
I was just curious because it didn't show up as one of the examples.
Yeah, it's just slightly
4,
worse.
5, 7. It's-
It showed up a lot in the calculation I was doing, then just always got beaten by
Yeah.
the different one.
that makes sense.
But I would see it as like some local maxima in some sense.
Right. Okay.
So do you have stability results?
So stability results are here somewhat annoying to quantify. Point sets can look very differently than just the combinatorial underlying 3 graph.
Well,
So-
it seems that the extremal configuration can be approximated by 3 poles, such that each of them are forming a equiangular triangle. So
Yeah, so this was in this one case. So, for most of those, for most of the corresponding hypergraph results, we know stability results or could prove them. For some of them, we have them at hand. For example, for the Balogh result, for this one, we have a stability like this is known. So for this one, would be quite easy to get. But for many of the other hypergraphs, you would first have to prove the stability result and then translate it back. So what one could do it, but it's a little annoying to quantify, in my opinion.
There's a different kind of stability you could consider is what's the largest epsilon that achieves the minimum. So for example, for an equilateral, for this unit triangle, maybe you would get something that's almost square root of 2 minus 1 would be the largest you could hope for, or maybe half of that, I'm not sure. I'm saying that
Yes.
some
So,
geometric stability, not the combinatorial.
right, so essentially,
But if you had like this almost right triangle, then of course epsilon has to be very, very small in order to achieve the minimum.
Mhm. Yeah, okay, maybe I didn't quite follow. So is your suggestion to, instead of looking at a single triangle, some like triangles which are close to the given one, and then ask that question?
No, just say you define you've got some function of the triangle and some epsilon, and
Yeah.
then you say you minimize over all epsilon, and this
Ah.
gives you a function that doesn't depend on epsilon.
Yeah.
Well, you can ask, what is the largest epsilon for which the first function is equal to the second
Yeah.
function? And
Um,
that would depend on the triangle, of course. It could be quite large for example, for an equilateral triangle, it might be quite large.
yeah.
But if it's an almost right triangle, it would have to be very, very small, something like this.
So for the 60-60 triangle, for this one there are results which says if all angles are between 59 and 61, then the answer is this guy. So there are results like this, and one can look at them. Yes. So maybe I have one small comment about an open question. In this theorem, it was about congruent triangles, but you can also count similar triangles. And the thing what you can change then is inside each blob you're allowed to iterate roughly, because similar, it doesn't depend on the scaling. And there's work on it. We managed to answer that question for the unit triangle, which is in the last bullet points. But roughly similar gets significantly more difficult. In heuristic, you can take each of these constructions, iterate. Not quite, but if you are familiar with with extremal combinatorics, then iterated construction, they're always a little bit scary. They are difficult to achieve. In particular, using hypergraph Turán results, this is sometimes not the right way to go. Yeah.
Is there any difference between we define a problem a little differently, like we can same point, we can point multiply and we just remove epsilon stuff, then is it the same problem?
Okay, I'll rephrase the question. You're asking, is the multiplicity version the same one? So I think yes, but it was a little annoying to prove. You can ask the same question in this weighted sense, where for every point you have a number associated to it, and our key number roughly reduces this to this one, so it should be equivalent.
maybe we should just continue asking questions during the dinner. So let's first thank the